Okay, so let's go through these questions. So, question 3. To demonstrate simple harmonic motion. So remember, simple harmonic motion is the mass that oscillates. So this is the mass of the trolley itself. Is the mass. It oscillates between of the two springs over here. So a student attaches a trolley to two similar stretch springs as shown in figure 3.1. The trolley has mass m of 810 gram. The trolley is displaced along the line of the two springs and then released. The subsequent acceleration of A of the trolley is given by the expressions A equal to minus 2k over mx. Okay, normally our equation is A equal to minus omega square x. So now they give different form. Okay, so no matter how, we continue first. Where the spring constant K for each of the springs is 64 Newton per meter. That means the K lah. The K is 64. 64. And X is the displacement of the trolley. Show that the frequency of oscillation of the trolley is 2.0 Hertz. 2.0 Hertz. So what we can do is, it depends on how familiar you are with the formula actually. So for this case, we make use of the omega to equate with 2k over m. 2k over m. Okay, we don't want the x, we have x on both sides, right? So we don't want the x. We just equate this with that. Okay, now let's write down. So from A equal to minus omega square x and A equal to minus 2kx over m. So they are equal to each other. Then I simplify the equation. I cut the x on both sides. Cut the x on both sides. Cut the negative on both sides. And then I will get omega square equal to 2k over m. And the other formula that you need to know is omega equal to 2 pi f. Now, omega equal to 2 pi f. So 2 pi f square equal to 2k over m. So expand 4 pi square f square equal to 2. The k is 64. The m is 810. So we change to kg 0.810. So you have to find the frequency. We get 2.0 Hertz. Okay, so this is the first part. Now let's move on. On the other side, B, the maximum displacement of the trolley is 1.6. 1.6. So this 1.6 is x naught, maximum displacement. So calculate the maximum speed of the trolley. Okay, so what we can do is, if you remember our discussion of the formula just now we have something like this, right? Imagine you have, okay, let's say you have x equal to x naught cos omega t. Then you differentiate, become dx dt, right? And then here become negative x naught omega sine omega t. Then I say the x naught omega is the v naught sine omega t. So based on this discussion that we did just now, so we know that v naught, maximum velocity or maximum speed for this case, is equal to x naught omega. Okay, so because of that, you can write down straight away v naught equal to x naught omega. and then we substitute. X naught is 1.6, sorry, 1.6 cm. Change to SI unit. The omega is 2 pi f. So 2 pi, so remember omega is 2 pi f. F is 2.0. We prove it already. And then you will get 0.201 meter per second. 0.201 meter per second. Okay, now let's move on. Part C. The mass of the trolley is increased. The initial displacement of the trolley remain unchanged. Suggest the change, if any, that occur in the frequency and in the maximum speed of the oscillation of the trolley. Okay, so let's think about it. Mass increase. So you know we have from the first part just now, we have, okay, let's take a look here. Imagine this part. We have 4 pi square f square equal to 2k over m. Okay, so imagine that. I write this down. So imagine that 4 pi f square equal to 2k over m. So now the question is saying that you are increasing the mass. Increasing the mass. So what happened is this one will decrease. It decrease. So you know in a fraction, if you increase the denominator, it will make the value decrease. So the value decrease, the frequency will decrease. Okay. So this is where they ask for frequency. So frequency decrease. Decrease. Okay. Then maximum speed. Maximum speed, what can we think of? Maximum speed. Okay. This is the formula. V naught equal to X naught omega. Omega is 2 pi f. So if I use these, I will get V equal to 2 pi f X naught. Okay. Now the question said the initial displacement of the trolley remain unchanged. So that means this is unchanged. This is constant. But we know that the frequency decrease. The frequency decrease. So the V naught should decrease also. Decrease. Okay. So settle for this question. Okay. 6.4. Graphs of simple harmonic motion. Okay. Now, you know our equations of simple harmonic motion. We have two set one. Okay, we have two set. So if the equation is x naught, okay, if the equation is x equal to x naught sine omega t, then the graph will be like this. Will be like this. Sine graph. Yeah, it will be sine graph. So here will be x naught. X naught is also amplitude. So that's why you can see this graph that use amplitude. Okay, so here is x, here is t. It's a sine graph. Okay. If you are wondering what value is this, why they put 2 here, why they put 1 here. Okay, so to understand this, first we need to know they make one round in 360 degree, or in radian it is 2 pi. Okay, it is 2 pi. Yeah? So if you put it here, okay, imagine omega is 2 pi. Omega is 2 pi over t. 2 pi over t. Yeah? So let's say I write down x equal to x naught sine omega is 2 pi over period time t. Yeah? So if t, the capital T here is period. So if the period is let's say the period is 2, if the period is 2, okay, period is 2, t equal to 2, I follow this graph, you see this graph, one period that take 2 seconds. So let's say this one I just follow the same, period is 2. Okay, then my equation is x equal to x naught sine 2 pi over 2 times t. So my equation is this, and then if let's say your time is, imagine if let's say your time is 1, if your time is 1, 1 times pi is still pi. So basically this 2 you can cut away, this 2 you can cut away. Okay, so now imagine that t is 1. So 1 times pi is pi. Sine pi is sine 180. Sine 180, yeah? Sine 180 is 0 actually, which refer to this point. So we know that this point is 1. So how about this point? This point is actually 2. It's actually 2. So why 2? Imagine when t is 2, 2 pi. 2 pi is 360, which is here. Okay, so this point is actually 2. Okay, 2. So the equation is like that actually. So which means at the end, after I simplify the equation, is x naught sine pi t. So where the capital T, the period is 2. So we get this graph. How about this graph? This graph is actually the Cos graph. The Cos graph. If let's say I write the equation here, this graph is actually x naught cos omega t. Okay, where again, x equal to x naught cos, the omega is 2 pi over t times t. And let's say the t is 2. For this case, the t is 2. Yeah, the t is 2. Then we get x naught cos 2 pi over 2t. So x equal to x naught cos pi t for this case. Okay. So that's why when t equal to 2, you get 2 pi. 2 pi means the cos move one complete oscillation. Okay. So now the next graph is the velocity graph. So velocity graph is where you have to do differentiation. So imagine after differentiation, we already discussed this. So we get v equal to minus omega x naught sine omega t. So that's why the graph is a negative sine graph. Sine graph is start with a mountain. This is the mountain, followed by a lake. So this one is the other way around because of the negative. This negative make it reflect. So start with a lake, followed by a mountain. So if this is the case, x naught sine omega. So after differentiation, you get v equal to x naught omega cos omega t. So in that case, right, your graph will be the cos graph. The cos graph will be like this, where here is x naught omega, and here is 2. This is t, this is b. Okay, so yeah, the graph will be like this then. Okay, now let's look at the next one. The next graph is acceleration graph. Acceleration. So acceleration is where you have to differentiate one more time. So imagine when you differentiate, this one differentiate, this one differentiate again. Okay, so differentiate the omega t, you get omega square here. So acceleration equal to minus omega square x naught cos omega t. So this is a negative cos graph. A negative cos graph, so that's why it is the other way around like that. The other way around. You know, cos graph is start from maximum, go to minimum, then go back to maximum. Maximum, minimum, maximum. This is the other way around. Minimum, maximum, minimum. It's the other way around because of the negative. Okay, so if let's say this graph, I differentiate it. So I will get A equal to minus x naught omega square sine omega t. So the graph will be the negative sign graph. Negative sign graph is like this and like that. So here is 2, here is t. So you get negative sign graph. Okay. So the shape of the graph depends on the equation. It is not always fixed to be like here, like in the note. It can be this version. Okay. Now let's move on. Energy in simple harmonic motion. Okay. Again, they use the pendulum bob as our example of simple harmonic motion. Of course, you can use other example like the past year question just now. You can use a trolley oscillate in between of two springs. That is simple harmonic motion as well. So let's discuss this. We want to see the conversion of energy when they oscillates around here. So at this point, right, this point is at the highest point in terms of its altitude, in terms of its height. This is the maximum height. So at maximum height, it has maximum potential energy, and then the velocity is 0 here, right? So that's why the kinetic energy is 0. Okay, and then after that, at this point, it has the maximum kinetic energy because velocity is maximum here. And then potential energy is 0 because at this point, in terms of height, this is the lowest. Lowest means the minimum potential energy. Okay, so at this point, we have the greatest height again, same as here, maximum potential energy, and velocity is 0, so that's why it's 0 kinetic energy. Okay, so now let's move on. Okay. Now let's see kinetic energy. So they are trying to derive the formula. So kinetic energy, we have V equal to plus minus omega square root of x naught square minus x square. Okay, so if you still remember how we derived the formula just now, where positive omega square root is for, okay, positive omega square root is for the sine one, start with sine, then you get positive omega. So negative omega is the one that start from cos. Okay, this graph is negative. So no matter how, kinetic energy is 1/2 mv square. So no matter it's plus or minus, after you square it, the plus minus will disappear. So then you square this, it becomes omega square, as in here. Then you square this, the square root disappear and become this. Okay, so we start from this formula, and no matter which situation is that, end up with this kinetic energy. Okay, kinetic energy is this formula. So you have to remember this formula, and we will apply it in partial question later. Now I just put a box here. Okay, total energy. So to know total energy, right? So we need to derive it also by using our pendulum bob here. Okay, we already know the kinetic energy having this formula, and then let's start from 0. Okay, let's start from mean position. Start from a place where x equal to 0. X equal to 0. So at this point, it has maximum kinetic energy. Maximum kinetic energy. So since x equal to 0, so you can substitute 0 here. By doing so, then this part gone. Only x naught squared remain. Then the half m omega square x naught square is actually the maximum kinetic energy, and at the same time it is also the total energy of the system. Total energy is half m omega square x naught square, which is this part. Okay, it's the total energy. We make use of the total energy here to find out the potential energy. So let's see. Potential energy equal to total energy. Potential energy is like this. You use total energy equal to kinetic energy plus potential energy. So potential energy is total energy minus kinetic energy. Total energy is this one. It's this one. Kinetic energy is this one. Then imagine you simplify. Imagine the half m omega square you multiply inside. Okay, you multiply into the bracket. So this time this, and this time that, and you simplify it, and at the end you will get this as the potential energy. Okay, this is potential energy. So remember the formula: potential energy, total energy. Okay, so altogether there are 3 formulas. Now let's see the graph. So total energy, which is this equation, m is a constant, omega is a constant, x naught is the maximum displacement, which is also a constant. So everything is constant here. So that's why the graph is a horizontal line. The E total is the horizontal line. So let's say I call this, I put some labeling here. I call this equation 1, equation 2, equation 3. So this horizontal line is equation 2. Then after that, let's see equation 1. Equation 1, kinetic energy. Kinetic energy. So you see when x equal to 0, it is maximum. So which is this point. When x equal to maximum, kinetic energy is 0, which is here. And here also, this point is here, point A, 0 kinetic energy. So that means this is a negative quadratic graph. As you can see here, negative x squared, right? So negative quadratic graph. Okay, negative x squared. This is not counted because this is a constant actually. It's a constant. So negative x squared means a quadratic graph that is set phase. So which is this graph. Okay, and if you look at potential energy, obviously this is the other way around because this is x squared. Positive x squared is a smiling phase graph. So through this diagram you can understand it also. You see maximum potential energy at the site here and here, maximum, and minimum potential energy in the middle, as you can see here, zero potential energy. So which is here, and the graph is the quadratic graph, x square, positive x square. Okay, so this one we settled already. Now let's see past year questions.